Welcome to another NERC's Coffee Talk. Today's agenda will be to cover Thevenin networks, sequence impedances of common items, single line-to-ground faults, transformer phase shifts, and phase-to-phase faults. For more information regarding the sequence components and their transforms, visit www.nercspower.com for a short coffee talk covering this. The first tool needed to carry out analysis of unbalanced systems with symmetrical components are Thevenin networks. A Thevenin network consists of a voltage source and a series impedance that is a reduction of the network at a node to just these two components. It is how the rest of the system looks to a node. When doing studies, a utility will often provide the Thevenin impedances or instead the available 3- and single-phase fault currents. The networks allow the analysis to be focused on the area of interest. The reduction might be just to a single voltage source with a series impedance or to two networks, like for a fault on a line where both ends of the line are of interest. The sequence impedances for cables and conductors can have several models: short line, medium, and long line models. The differences between the models has to do with how they handle their phase-to-phase and phase-to-ground capacitances. The short line ignores the capacitance, the medium line models it with capacitance on each end of the line, and the long line distributes the capacitance along its length. Short circuit and power flow programs often use the medium line model for transmission lines. The positive and negative sequence impedances for cables and conductors are equal due to the selection of the phase rotation being an arbitrary choice and being passive components. When modeling these components, it is good to keep in mind that as the spacing increases, so does the positive and negative reactive impedance. You can remember this by the fact that if there was zero spacing and you drew an Amperian loop around the three conductors, the sum of the current would be zero, so the magnetic fields would be zero. The closer the spacing, the more magnetic field cancellation there is and thus less reactance. A consequence of this is that cables tend to be much more resistive than spaced-out transmission lines. Likewise, with zero sequence impedance, the field cancellation reduces the closer the spacing of the conductors due to all three components being in phase. Positive and negative capacitance decreases with increased spacing and zero sequence increases with spacing and closeness to ground. Transformers are passive components like cables and conduits. Both their positive and negative impedances are equal. Their zero-sequence impedances are often estimated using rules of thumbs. What makes transformers very different from the other items we talked about is that how they are wired can determine if they block, path, or source zero-sequence current. If a transformer blocks zero-sequence current, like with a delta-delta transformer, zero-sequence current can't flow through it. This is represented in the zero-sequence network as an open circuit. If it paths zero-sequence current, like with a Y-grounded transformer, zero-sequence current can flow through it. This is represented by a series impedance in the zero-sequence network. If a transformer like a Y-grounded delta transformer sources zero-sequence current, it provides a means for zero-sequence current to flow into the grid. This is represented with a shunt connection in the zero-sequence network. Only transformers that have shunt connections in the zero-sequence model can provide zero-sequence current. For spinning motors and generators, the positive and negative impedances will not be equal. The zero-sequence impedance will depend on the grounding and how it is wired. Short-circuit programs will often ask for the sub-transient and transient impedances in addition to the sequence impedances. For generators, they will often require the P and Q limits, which can be gathered from the generator capability curves. Inverter-based generation includes solar and Type 4 wind farms. Type 4 wind farms convert the generated AC from the wind turbines to DC, and then the inverter injects AC currents onto the grid in any of the four quadrants. This AC to DC to AC conversion decouples the wind turbine from the grid. Often the limitation on the contribution of inverter fault current to a fault is a thermal limitation and in the range of 1.1 to 1.5 per unit. Some regions have low voltage ride-through curves, which are used to determine how long the solar or wind farm is required to contribute fault current to a fault before shutting down. In areas with high penetration of inverter-based generation, it is essential for the inverters to provide fault current and VARs so the fault can be cleared by the relaying and the system voltage doesn't dip excessively. The behavior of an inverter during a fault is determined by how it is programmed and could be a talk all by itself. In relation to symmetrical components, it is just important to be aware that an inverter may be modeled as a current source and may or may not provide negative sequence current depending how it was programmed. Now let's go over single line to ground faults. All three sequence networks are in series for a single line to ground fault, and because of this, added impedance to ground can be used to limit the fault current for ground faults. This is how impedance-grounded and ungrounded systems limit ground fault current. This type of a fault accounts for over 90% of system faults, so if there is a network you are going to burn into your head, this is it. This is something that can be difficult to deeply explain without sequence components. Suppose you have an ungrounded system. The only thing that holds the neutral to ground is ground capacitance. That is a weak coupling. Not enough to hold the neutral to ground during a ground fault. When a ground fault happens on an ungrounded system, the neutral stays at the center point of the three phases by definition, but the ground moves to the faulted phase or phases. In the diagram on the right, it shows how a ground fault on VAG shifts the ground from neutral to VAN. This causes the phase to ground voltages to increase by up to a square root of 3 on the other two phases. The voltage shift of the neutral from ground is equal to the zero sequence voltage, which is exactly what you would expect from the sequence network for a single line to ground fault with an open connection in the zero sequence circuit. The phase to neutral voltages and phase to phase voltages stay the same. Delta wound motors can operate for this reason during a single line to ground fault, but they must be insulated to handle the higher voltages. Here are the voltage phasors you would see for a single line to ground fault on an impedance-grounded system with varying amounts of ground impedance. The amount of zero sequence voltage that develops is determined by how much the grounding impedance constrains the zero sequence or ground current. As the amount zero sequence voltage develops, the faulted phase gets pulled closer to ground and the other two unfaulted phases increase in voltage to ground up to a square root of 3 of their phase to neutral magnitude. One thing to keep in mind with single line to ground faults is how the positive and negative sequence current and voltage are shifted differently by a transformer. A delta Y transformer with a 30-degree lag from the delta to the Y side will cause the negative sequence to lead by 30 degrees. This can play an interesting role in how a fault looks on either side of a transformer. Here is a sample of some transformer connections and their phase shifts highlighted in yellow. The capital letter in the transformer's name designates which side is the high side and the lowercase letter is the low side. D is for a delta connection. Y is for Y. Z is for zigzag. The following number indicates the leading and lagging of the transformer's high and low sides with reference to a clock. There are 360 degrees in a full circle and 12 hours on a clock, and that comes out to 30 degrees an hour. For example, a DY11 represents a delta high side Y low side with the delta side lagging by 30 degrees. On a transformer's nameplate, the winding diagrams usually indicate the phase shift as well. This is the transformer connection we are looking at. A Y-grounded delta transformer with a fault on the Y side. Note that the Y side can source zero sequence in the shunt connection and the delta blocks zero sequence current with its open circuit. So, what do the fault currents look like on a Y-grounded delta transformer with a fault on the Y side? We know that the identity for a single line to ground fault is for I1 to equal I2 to equal I0. But the delta on the transformer blocks zero sequence current, but it will allow positive and negative to pass. This transformer has 30 degrees of lag and we need to shift the positive and negative sequence components in the opposite directions. This produces 60 degrees of separation between negative and positive sequence. So, What does this look like in the phase domain? The result of a fault on the Y side of this transformer that is supplying all the fault current is that the fault looks like a phase-to-phase fault on the delta side. A ground fault produced current that looked like a phase-to-phase fault on the other side of the transformer. Pretty unexpected. Now take a look at the sequence network connections for phase-to-phase faults. Only the negative and positive networks are involved. No zero sequence voltage develops or current flows in this network. This means that the neutral won't stray from ground and produce over voltages due to zero sequence voltage. Also, the available fault current won't be affected by the system having impedance grounding or being ungrounded. A system constrained to low ground fault currents will still have normal phase-to-phase fault currents. Here is a graphical solution to how the network is derived. There is no current on the unfaulted phase and the other two phases have current that is 180 degrees out of phase and equal in magnitude. The positive sequence network feeds into the negative sequence network with the opposite polarity. This produces the 180-degree shift between the positive and negative components. Here is what the phase and sequence components look like for a phase-to-phase fault. The blue and green phase phasors are 180 degrees out of phase. The current comes up one phase and returns on the other. There is no current on the unfaulted phase nor is there any zero sequence current. The positive sequence and negative sequence red phasors are 180 degrees out of phase. Here is what the network would look like for a phase-to-phase fault without a full Thevenin reduction. So you can inspect the voltages and currents on both ends of a line. Each parallel path is each side of the line. It is good to understand sequence networks. However, without software, it can get very tedious to have to calculate a solution by hand. For this reason, in my opinion, it is much more important to understand the general dynamics of sequence networks than at being efficient at performing hand calculations. Short-circuit software is an incredible tool that should be taken advantage of. But without understanding the underlying principles, it is hard to fully take advantage of the tool or to fully understand a system's characteristics. The tool created for animating the phasors will be posted on the website. For information related to what sorts of power-related services NERCS Power Consultants LLC offers, visit www.nercspower.com. Email douglas.milner@nercspower.com to be notified of new presentations. Coffee talks will be stored for later viewing at the company website. Thank you for watching.